Hi everyone, this is a new video on some of the CNCs that we're building here. I want to kind of give you a little bit of tour around the shop and kind of show you what we do. But also I want to talk about how this particular CNC that I'm going to show you hasn't ever been built before yet. It came straight from design, right out of CATIA, right into production. And you'll see, talk about it later in the video, that it was an unfortunate chain of events that caused me to have to remodel the entire design about a month before class started. And so I really want to kind of shine a light on how important 3D design is and how important the assembly workbenches are. If you have a product and you want to put it together, if I know that this part here, for example, is so long and I have to fit it between a couple other pieces, that well, it'd be kind of nice to know things like the tolerance, the fit tolerance here, and the next one, and the next piece that goes along with it, and the next piece, and so on, right? If you model your parts individually, you tend to you don't get that whole working in context kind of thing. So anyways, I want to kind of talk about that out there. Also, just what are the basic components of a CNC, a DIY CNC, if you will. We are on a budget, like everybody else in the world, so our choices are maybe not always the best because of that. Also, we're on a little bit of a time crunch, so if we have to get something that's really good, but it's going to take a long time to get here, then we can't get that either. So we'll kind of talk about that. There'll probably be also other videos on what we've done in the past, how we got to this point, because the first few classes, also that's kind of briefly mentioned in this video, that we started with a really kind of broad, I guess, idea on what we wanted to do, be it a mill, but we didn't have any idea where we're going to get these parts from, what the shape was going to be, how strong the motors need to be, and anyways, consequently, the class was a lot longer. It was great fun, though. It was really a great class where everybody was doing the research. Nowadays, we have it kind of figured out, for the most part, what the mills are going to be, and so then people kind of work off of that. We still do make all of our own parts, less, like the motors and the 80/20 aluminum extrusion. Other things I want to mention is this video, it kind of starts out like some of the things I've been putting into the impromptu incidents playlist, and it's pretty loud. It's kind of crazy, just sort of running around. But I wanted to show, I think it's important to show in a lot of these videos the rough edges. If I start scripting too much of this, like right now, you can probably tell I'm just talking, right? I have no real idea other than I got a piece of paper right there that has the bullet points on it that I want to say. I want to show the stuff where we are excited that something new just happened in our world, in other people's world, yeah, maybe it's not a big damn deal, but I want to show what's exciting to us, and I want to show it when it happens. So I put that in impromptu incidents. The other stuff that's training videos, I'll try to keep it into a different category so that you understand that this is, like in the CATIA videos, that's pretty straightforward training, whereas some of this other stuff might be freaking out, swearing and cussing and running around, oh my god, look at this thing that we just did, right? So hopefully that's kind of fun. But anyways, it is going to be very noisy out there, so the first little bit after I finish talking here, it's going to go into shop noise, and you're going to hear me yelling over the top of this router that this student chose. The router in particular is, I don't know, it's probably like a 1970s hand router that they put into here, and they were completely okay with it, so it's pretty loud. I think it's probably running at about 15,000 RPM. Understand that was a student choice. We give them that choice, whatever spindle they want to have. I would opt for something like a little bit more controllable spindle. They sell these VFD, who is it, Hunyang, I think it is, out of China, makes these spindles. They come with or you can get a VFD and a really nice spindle that it controls, the VFD controls, and but I mean, they're about $450, and so far as of yet, as of anything coming from China, we don't really know if long term these things continue to work. So far so good for about a year on one mill that I'm running, so I don't know how well I can actually promote that. The other side here is we go with, like, we were talking about a laminate router, but maybe get something like a Makita, or Porter cable, or anything that's decent, maybe local to you, that if there's anything wrong you can get an upgrade, and very particularly something that's got a speed dial on it, a speed knob. If you don't have that, then you can also buy these little kind of like dimmer switches, basically, that you can plug in line with your device. Some devices take to that better than others. So anyways, that's an option. The other thing with the router of choice that you use, if you use a router for a spindle, I've been opting for the ones that have kind of a sleeve that you can take it out of, and it's a metal casing. That metal casing makes it a lot nicer for us to make a clamp to grab a hold of the thing, rather than just a plastic case. Whereas if we want to squish it real hard, we're probably going to squish it and or affect the angle of it, because if you grab it on the plastic and it kind of bends a little bit, maybe that's going to send the spindle into kind of a tweak. So one last thing, in the video you'll see that we're pretty happy because the previous mills were good for wood, they were good for machinable wax, they were good for softer things like that. We've never said that they could cut aluminum. The problem was chatter. The main vertical beam, because we have a moving vertical axes on this, it starts to shake, and you'll see me again in the video kind of describe this, but the vertical piece comes down, and as you cut through the metal, it wants to deflect back and then snap forward, and that happens really fast, and so you get this chatter trying to go through the metal, and then all kinds of other crazy stupid crap happens after that. These mills, very excited, they're very tough, and they cut through aluminum no problem whatsoever. And you'll see that in the video. But what we did after this was we said, well, what the hell, we better try some steel. And so then that's what this is. We threw just this hunk of steel in here, and see if you can see this. It cut very nicely. We were coming down about 5 thou per pass on it, and then here's a little pocket that we put into it. The mill itself, we don't have really fluid on it, we were just spraying coolant on it, and but anyways, it works. So we have a new mill design. It was I designed it in CATIA a month before class started, never built a prototype, went straight into production. It is very solid, cuts basically anything so far, that you'd mill in your traditional shop. We're cutting plastic, cutting wood, machinable wax, aluminum, steel. I'm sure it would work with stainless. It just is, kind of a matter of what cutter you have. Alright, so we'll go ahead and go out to the shop, play the rest of the video there. Like I said, remember it's kind of loud, so but bear with, it's probably about 2.5 minutes, and then after the students are gone, when everything's kind of shut down and it's quieter, I grab the hand cam and go through the rest of the explanation. One other thing that I wanted to mention in this, I might not have even uploaded this video, so it is really kind of just a kind of an off-the-cuff thing. But it was a reason for me to use this new editing software. It's Kdenlive. Recently switched everything over into Linux and going more and more open source. Always trying to do that, can't always, right? So anyway, so I've been messing around with that. Look that up if you like. It seems to be pretty good. It's got, the typical open sourcey kind of problems. There's a lot of conversation online, typically things like there's some icons that don't show up, and you have to do some stuff to get that to work. It's a little bit different. I've been using Adobe Premiere for, I don't know, probably since the 90s, maybe early 2000s, let's say that. So anyways, that's another thing that's going on here. So if the thing is a little bit weird, maybe that's why too. We'll see how it goes. All right, out to the shop. If you can hear me, this is the first milling of aluminum on the brand new mills. Let me get around Ed here. Here's our program. Here's this super high-tech spindle motor. So far it looks like it's working like a dream. Other than I can't hear crap because of this damn router. It might not be cutting, it might just be melting it away. Get a look at the whole thing here. So because of a last minute change of events, chain of events, we were missing a bearing, so we ended up finding linear rail, thankfully, for really cheap, for about it was less than $100 for a set of 2 rails and 4 slide blocks. We added in our lead screws here, manufactured everything on here. Nice routing. The wooden table is just for extra height, and he's sacrificial. He can tear it down, do whatever he wants with it. Adding in all the nice flex track here. Right in here, if you can see that in there, see if I can yell at it and zoom in. There's a thrust bearing inside there that really helps, rather than metal on metal. Excellent, first run. Holy crap, it's milling day. So here we are over the other mill. This one, of course, hand built as well. Had lots of videos on this one before. Here we are cutting out a longboard. Looks like it's running well. Then, over here, we're cutting out holes for longboards. So we cut out the holes over here, like so. And this gives us the profile, the pins that we can use over in the other mill that we just came from. As there's a fixture there we can set it into, lock it in place, and then we can cut the profile out. And then back over here, crazy mill running again. Busy, busy day. All right, now that's a little bit quieter. I can show you kind of what we were doing with this. So this is one of the other things I do. We build CNCs. I teach class on how to put this together. So the class is, yeah, we're building CNC machines, but what I'm trying to show people what to do is automation of any kind, right? So as far as the, you know, X, Y, and Z coordinate thing, moving something down a track, I mean, this could be anything, you know. This could easily be, you know, a camera rig to slide, you know, a camera along. It could be a delivery system. You could have some of this fully supported rail track right here, and you could have this in, you know, mega lengths and slide, you know, parts from one place to another, depending upon things like, you know, maybe a microcontroller senses the load, or you break a beam and it says, oh, something's here, and then we're going to go move it down to the other person, right? So that's kind of what the class is about, but I just want to show off what we have going on here. So some of the first iterations of this, these mills, when we first started out here, I started a class, believe it or not, I start classes like this, of, hey everybody, don't know what we're doing, let's figure it all out. So we had one course, it was about 6 months long, and we spent probably about a month just figuring out what it was we were going to do. But the deal with that is it's all the stuff that you can't get in a regular class. You know, it's like, hey, here's this kit, pour it out on the table and put it together. Isn't that great? You know, that you're able to build a kit. You know, just like you built a model when you're like 6. So, for example, you know, here's our typical, you know, standard stepper motor, which, I mean, standard for us is probably kind of big for most, you know, hobby projects, but NEMA 24, kind of a high torque one. But where do you go to get that? There's lots of places. How much torque do you need? You know, what's going to be your micro steppers, and then that, or steps, and that gets down over here into your drivers. There's your driver boxes, and then your control board. I've been getting these a lot. I really like this place. This is from Planet CNC. So they developed this, you know, years ago, and they've had many different iterations. But what's nice about this is I mean, it looks like any hobby project, right? And for me, I feel like this is a great, you know, hey, look, somebody started a company and is becoming pretty successful at it. You know, it's that kind of a story. But the other thing is that, you know, I don't know if you know, they're just also, you know, this multi-talented company where they can put this together and make it work and then write the software for it. But the software that they have here, if you like Mach 3, I feel that it's a bit better than that. It's really nice. So we have the fully supported rail here. The first iteration we were using V-Rail and some other stuff that we got from openbuilds.com, and that place was really great. It was a great find. There's a lot of story that goes along with that, you know, how we found all this stuff. Well, you know, we made some things before we found something, then we found something, and they're like, oh, hey, let's add that onto it, but then that thing causes another change, so on and so on. This lead screw, I mean, sorry, this fully supported rail was very expensive. When we first looked, we were doing this class almost a few years now. When we first looked, it was not cost effective. We couldn't get it. Then we went with a different design, a different linear motion, and then we kind of changed a little bit again. And then just before this class started, 1 month before this class started, this is, by the way, why I'm showing this, because I'm pretty damn happy about it. One of the V-bearings, the V-bearing supplier for the slide that we had before, they didn't sell them anywhere. I looked around, I couldn't find any. Sorry, I could find some, but they're way more expensive. So it's like this little bearing. I mean, it's probably about, you know, barely an inch in diameter, and this other company was like $12 a piece, and we need, I don't know, probably 24, 26 bearings per machine, and so that was just way out there. So then I started looking around again, and lo and behold, you know, thanks to, you know, whatever, robots, this is incredibly cheap now. So I could get 2 of these and 4 slide blocks that you can see underneath here. Sorry if I shake the cam, I'm going to reach over and grab this other one. One of these things right here. So again, you get 4 of those and 2 of these rails right here, and these are 700 millimeters, and I think it was around $100. So that was definitely doable. The thing that we get from that is an incredible amount of stability. So if I grab this and I want to wiggle it around, I mean, this is tough. This is all very secured. When you pull on this really hard, the only thing you can get to flex is really just the plastic that's inside of those slide blocks there. So super great. So let me kind of cut to the chase here. This one we were really happy about because all the other mills we built would cut wood, they'd cut plastic, but we wouldn't say that they would cut aluminum. Even though what happens is when you build the CNC here, it's not necessarily things that a lot of people think, you know, right off the bat, oh, you know, maybe it's your motor, you need a better motor, or you need more torque on something, you know, like maybe, you know, your steppers or something. But what was happening was, if you can imagine this slide, whatever you have for a slide, anytime you have this movable Z-axis, right, as opposed to a knee mill where everything is solid rigid and the table moves, when this thing starts moving and it starts descending here, this, as you cut through the metal, this would start to bend. Now, this is minute. I mean, it's not minor. It's friggin' horrible. But it moves just a tiny little bit. But as you're pushing through the aluminum, if you could see it on high speed, it would push through, it would flex back just a little bit, and then it would snap forward. Flex back a little bit and snap forward. Now, it's doing this in probably about millimeter increments, and it's going a lot faster. So what you get is just chatter as it's going down here, and you can't hold a line, and it's a bunch of shit. So no good. So this right here, super solid. And what I was showing in the other impromptu video before was how I was cutting out this aluminum here, and I don't know if you can see this, but that's probably a bit better light. You get the ringlets from the end mill, but you know, ooh, it's really smooth, right? So it works really great. And this right here, also the guy that was running it just wanted to see how well it would do. So we took a 10 thou cut right through, a 20 thou cut right through, 30 thou cut right through. Felt like it was getting a little bit sketchy. It might not have been, but I was like, whoa, you know, normally when I'm trying to cut stuff out here, I'll drop down like 5, 8 thou at a time, you know. This did, you know, let's say 20 thou, you know, without any issue. 30 thou was also without an issue, but it just had a little bit different tone to it. And if you run mills, you'll know what I'm talking about there. As soon as something gets kind of a deeper tone, you start getting a little bit concerned. So let me show you around. Oh, I guess I should address this giant monstrosity right here. This is only to prop this up. He might leave this here permanently, but his point of view of this was like he didn't give a shit about the table, and he's just like, it's all sacrificial. He doesn't need things to be perfectly level and flat, so he says it's good enough. He went with a smaller router, so he needed to move the table up, and so that's why that's there. Now if I move over to here, his mill here, let me pull this out. Oh, this is kind of hard in this mess of a place here. So his mill here, this is another story. So we were running the typical little laminate router spindles, and then we found online, China manufacturing, they sell these really awesome, like I think that's like 1.5 and 2.2 kilowatt spindles here, and then the VFD up front for the control for it. Anyways, they're fabulous. We like them a lot. You can get, if you get an ER16, I think that goes up to about a 1/4 inch, but he wanted to get an ER20 because the collet here that comes with it can support up to a 1/2 inch shank end mill. So that was good. I believe on mine I have an ER18, which will do 3/8, which seem to be like the typical end mills I use are 1/8 of an inch, 1/2 of an inch, and or sorry, 1/8 of an inch and 1/4 of an inch, and every now and again some of the tools will have a 3/8 shank on them. There's a lot of ER11s out there, you know, so look around. That's one of the things. So if you're looking for a spindle like this, they're great, right? These ones happen to be water cooled, by the way, and I think that that's a really great feature. There's other ones that are air cooled, so there's kind of difference, and I'll tell you about it. But when you look at it initially, look for the collet size, and check out, you know, think about what kind of end mills you're going to use if you don't know. It's not necessarily bigger is better and you want to get the biggest one possible. I mean, I have a lot of mills around me, and I still primarily just use, you know, 1/8 of an inch and 1/4 of an inch. But, you know, that's your deal. You might have something different. Now, the water-cooled versus air-cooled, this is not, so some people are like, oh, water, that's for fluid. No, it's fluid, but it's to cool the motor off. So it runs in here, and there's a cavity, it spins around and squirts back out. You close this down, so it's a whole closed loop system here. Here's a thought for you that we were joking around and then sort of not joking around. If you've ever seen these, it kind of looks like a small motorcycle air filter, radiator. It's the heat sink, it's the cooling for CPU cooling for a PC that they sell, right? So if you can see kind of what I'm holding here, this rectangle that would fit like two 120 millimeter fans, they have radiators like that. And so we're thinking, I wonder if we filled that all up with liquid and we filled this one up all with fluid and just mount that damn radiator here, or maybe around the back right here over on this plate, then that could be your complete enclosed system. And the fans could be there and keep it nice and cool. And then you don't have to have, typically we'd have tubes running out of here and going down into the to a bucket or something. All right, so here's the other thing I want to show you about that spindle system. So you can buy them as a kit, or you can buy them separately. And if you buy them separately, just know that you need to have this. So this is your VFD, your variable frequency drive, and you'll see lots of these around. Now, here's the deal: when you're buying stuff on eBay or Amazon, either or, but you know it's coming out of China, and you find out, you see that there's a whole lot of variation, but there's a whole lot of combo stuff. Like I said, like you could get this as a kit with this with that, or maybe this with that, and a collet set and a holder and a whatever, or any variation. But as you look at all those different ones, then you kind of notice that, hey, you know, this one looks a little bit different than the kit that is, you know, the ones that are in that other kit. So if you dig deeper, you will find that a greater majority of these out here you're going to find are going to be for 240, and these ones are for 110, you know, 120. So if you're from the States, that's a big deal, and that's going to knock out, God, probably 90% of the VFDs that you see online. So keep that in mind. Here's the other thing: this plus the spindle and the you know, the fish pump or whatever you're going to get to pump all this, etc., the hose, you're looking at about 400 to 450 US dollars, and that might be a deal breaker compared again to over here, your little laminate router, which, well, actually I don't want to say like, oh, your little laminate router that's like free out of a damn gumball machine. They're still going to be about $100, $125, but you're just, you know, just plug it in and go. So that's an option. The thing we talk about, though, I talk about in class, though, to keep in mind is, let's say that you have, you know, any kind of a product, and you got the $10 product, and it's okay. $20 is a bit better, $30 is a bit better, and it moves up in kind of like a nice linear, you know, quality, you know, steps. Then you go, oh, the $40, it's just that much better, that next step. Well, that $40 is $400. And you say, well, that's ridiculous because I only get, you know, yes, it's better, but it's not that much better. Well, that's ridiculous. It should be cheaper. Well, what if it's not? If it's not and you want it, that's all there is. So that's the story there to keep in mind. And so that's why some of the people have been going for this. Expensive, but for them it's worth it. And it's not, believe me, when they spin, they are pretty much silent. They have almost no vibration. And again, the water cooling, so it's going to keep it nice and you know, running well for a long time. I have one on my large mill that I've been running for about a year now, and it works just fine. All right, moving on. So here is the cable track that you can add on to. This is, well, there's a big deal right there. Cable track, that's the key word to find, because a lot of times you know what it is, you've seen it before, but you don't know the word. Look up on Amazon. I mean, everything, you know, it comes in different dimensions, width and height. Think how many wires you're planning on running into it, and like this one's larger because he's going to be running the water in there for the spindle. It's around $15 to $25, maybe a meter. It's pretty cheap. So you get this stuff here. These can break out of here to help you run it, or you can just feed it through, and then just make some brackets and mounts to hold it, and then run your stuff out there. Since I happen to be right here, these again are the NEMA 24 stepper motors. I was getting the bipolar motors, but they went out of stock. This is at Steppers Online. So that's the place where we get these. We were getting them before from another company in the States. We're in the States. And just to give you kind of a thought here, they were a little over $50 a piece, which might not sound like much. It's a nice motor. So then we found Steppers Online coming out of China, and they are $25 a piece, so half the price. It did up the shipping, but not even close to enough to warrant even thinking about going to the other company. All right, and so anyways, these ones here are not bipolar, but we wire them in bipolar series, and so that's why what you see here, if you ever do anything like this, look up your data sheet. You essentially imagine that you have 4 coils inside of here. We wire 2 of those coils together in series to make, let's say, a larger coil, and then you end up with only 4 wires coming out. In most CNCs like this, you opt to have the torque rather than the speed, and incidentally, that's not a sacrifice. The speed is plenty well fine. So this is the control portion for the big mill. I've done other videos on this. See, the one that I use for cutting out long boards and snowboard bases and all that. So I want to give a quick overview on what this does. Just kind of a real short and simple thing here. We have a little brain. We have our microcontroller. Here's essentially the steps. You have microcontroller, puts out little signals telling something to do something. Then we need to take that little signal and turn it into a bigger signal to do some work. Okay, that's pretty common in all kind of microcontroller projects. We need to take something like a 5 volt, 3.3 volt logic and turn it into, you know, even if it's just like 12 volts, like the little mini mechanism car, or a robot arm, or, you know, a man lift, right? Or, you know, 120. We could do that too, 120, 240. So we're usually talking relays at least, if not, you know, something a little bit more advanced. So here's the chain of events, sort of. So here's your microcontroller. So here's your board. And if you look at this, I mean, it really is not a hell of a lot different than any kind of a development board or project board that somebody's put together. So you have your chip, and then you broke it out, you know, broke out all the pins here, and so here is your different axes, 1, 2, 3, and 4. So this actually has a, sorry, with my fingers, 1, 2, 3, and 4. So this has got a 4th one here that you can send out to whatever you want to do the little 4th axis rotisserie or what have you. Also other things for limit switches and emergency stops. So again, pretty common breakout board. The USB is providing the power in this case, or if you needed to, you could add in an alternative 5 volts, which is usually a good idea, but I haven't had to do that yet. Okay, so you take the little signal out of here, the little boopity boops to tell it to do a thing, and then we're going to take that signal and we're going to run it into what we call driver board. So the driver box is here. So the drivers are kind of like, you could think of them a bit like a relay, and they're taking the little power and telling the big power to go out instead. It also does micro steps, and we'll talk about that more in a second, but they allow, basically with a single microcontroller, typically you just have it doing one step at a time. Micro stepping allows it to kind of divide steps up between those steps, you know, micro steps. So anyways, controller sends out 5 volt signals here, going into these guys here. They need to mix that in before they send it out to the motors with the big power. So here's your big power here, and so this one here is a 36 volt, the other one you're using is 24, but these ones, the drivers put out 24. Whatever the motors need, really, right? So 5 volt here, big power here. These go together into a driver box. The driver box pulses the big power based upon what the little power says, and then spits that out, the wires here, which run out, and then they go over yonder, you know, to your motors. So that's the process. It's not really terribly too complicated. It's again, it's a pretty typical situation with automation, robotics projects, whatever you want to say here. I will mention a thing that's kind of neat. You know, make yourself some little standoffs here. You can see what I did. Hot glue everything together if you want. Zip tie it if you want, and route it nicely. As a bit of a habit, anything that's even remotely logic, you know, some kind of a digital signal here, I try to keep that away from any other larger power, especially like your mains here. So this is 120 going into it. I would like to keep it away from that. And another habit I picked up from somewhere along the way. I never run mains, especially parallel with anything, for very long. So if I need it to be there, I'm going to get it around it and out and try to cut through it here, because the way I've always figured it is the amount of induction, the amount of field that's coming off of it. You know, it's kind of a duh again, but as long, you know, the longer you spend along it, the more you're possibly going to affect the signal in there, if not even just attenuate it and make the distance that it can go shorter. Alright, so back to looking at these driver boards again. The thing I want to mention about this, there's some relatively obvious stuff. When you go to find yourself a driver, I say board, but box, whatever, H-bridge, this needs to have the power to match the stepper motor that you have. And so the stepper motors we get, I think they're like 3.2, 3.4 amps possibly, and make sure that this can accommodate that, which these ones here do just fine. Let's see, so if you look right here, you can see that you have a table, and I guess I should have looked at one here that didn't have the tape on it. Yeah, let me spend some time picking tape off. Alright, that's better. So you set your dip switches to these values right here. So if you want to change the current, you just say, you know, off, off, on, off or something, and then you get a little bit more, a little bit less. And then the micro steps is how many steps. And a stepper motor, you have basically these pointy magnets, and this is going to be real hard to explain with one hand on the camera, but the pointy magnet moves from one pointy magnet to the next, to the next, to the next. And a micro step will allow you to float between there. If you're just moving step to step, like we do this in an exercise with one of the robotic classes that we do, where we make our own H-bridge and you run it through a microcontroller, you get to go one step at a time, and the motor is fairly, it moves okay, but you can tell that it's got kind of a step to it. It's kind of a as it moves, as opposed to a nice smooth motion. So these will allow you to smooth that out. But the way that it works is, again, if you send just pulses to it, it's like one pointy magnet to the next pointy magnet to the next one to the next one. The micro steps in here allow it to say, okay, well, I'm going to give, you know, maybe 75% power to the other magnet, or this one, and then maybe 25% to the other, and it causes you to kind of, the pointy magnets sort of float between each other. If you look up the data sheets on these, they'll talk about torque loss on that. The finer the micro step, the more your torque curve is going to drop down. So far that hasn't been a horrible big deal. You know, as the torque drops down, then maybe you can bump the current up a little bit more, you know, and it's sort of a balancing game. Matter of fact, it's a big balancing game, because there's this, and then there is the software as well. So yeah, so if you were to, for example, crank up your microsteps and you want to turn up your current a little bit, back and forth, and sometimes we'll crank the current up, and then we'll grab the motor and we'll kind of, or you know, the moving gantry, we'll hold on to it and see if we can stop it, or we'll just have the motors on, put a wrench up to the shaft and see how hard it is to turn. Incidentally, you can probably always turn a stepper motor that's on one of these. I don't think you need to have so much current that you absolutely just can't move it with a wrench. You already have enough leverage with the lead screw for it to operate the mill cutting through metal. It shouldn't be to where you have to like have it on that hard. Anyways, you change your micro steps, maybe you move those up a bit, then you move the current up a little bit, then you move these up a little bit, then maybe turn that up a little bit, and then at some point in time you want to come up here and you want to just feel the motor and make sure that that thing is not getting smoking hot. Okay, warm is usually okay, hot not so much. If it's actually getting hot, if it gets hot after you've been running all day long, maybe that's acceptable. If it's getting hot after you ran it for maybe 5 minutes, hot to where it's a little bit uncomfortable to touch it, then you probably want to come back and check your current chart, and then possibly even change your motor if it's not working properly. So here's the couplers we're using. These are, in most of the industry, they call them Lovejoy couplers. In other places you'll see them as flexible jaw couplers. These ones are really nice. There's a rubber plastic bit inside here that they call a spider, and the idea is that this is separate from this, and it allows it to possibly, for one, this could like flex and move a little bit and it won't translate that motion hard to the motor. And the same with any kind of vibration. If the motor or anything out here is shaking a little bit, it creates a little bit of a brake buffer, if you will. And we get these also from Steppers Online. I like these. Okay, this is a silly little story here. I like these because the other ones that I got were black, and black, and just kind of like they just fell out of the machine. These ones here from Steppers Online, they're nice anodized aluminum, nice bright red spider. Not that that matters, but it looks nice. Each one in its own little Ziploc bag, in its own little box, all packed in a big box, really super nice. So pretty good purchasing experience there, I guess. Here we have the side of the gantry vertical support plate, and I wanted to show here that these slide blocks, take note that if you use any of these, they have an adjustment screw up here and another one up on the top of the block. So if you ever feel like you want to make an adjustment, which maybe you won't, you need to make sure that these are up on the top, probably, right, rather than trapped underneath here where it might be a lot bit more difficult to get at. So we have these ones here and then the one on the top. And so then what we did is made sure that we made a hole in this so you have an access hole to be able to get at the set screw inside there. All right, here's the thing to think about when you're making, well, any of your axes. This one here, it's your Z, so it has weight on it pulling down. So you have to think, where's the weight going to in this? And the other thing, so that's usually pretty easy to understand. But the other thing is what if it goes up? What's keeping it down? And then you think, why do I need to keep it down? It's not like it's going to jump up in the air. Well, if you take this and it goes down into some stock and it starts pressing down into the stock, if the stock is a little bit hard, it'll cut through, right? And we're talking fractions of, milliseconds basically, not fractions of milliseconds, so we're talking milliseconds, bro. It's pushing down on it, and as it tries to push down, if it can't push down immediately, it's going to push something up. So what's holding that down? In this case, this will be kind of hard to get a picture of here, I think. Yeah, I don't know if I can show this here. The lead screw here, the lead screw is the Acme 5-star 10 TPI lead screw. It has an anti-backlash nut down buried in here. Good God. And then there's a bracket attached to this. Yeah, this is going to be real hard to explain. This motor assembly, all of this goes up and down with this vertical assembly. So if you think about it here, when this wants to go down, it's going to be trying to pull that lead screw up through, right? So what we needed to do was trap it so that wouldn't happen. And so then there is, you'll see, we have a little collar inside of here, and on top of that collar is the same as right here. We've basically trapped it on both sides, which is kind of the other part of the story I'm getting to, with a thrust bearing. And for stuff like this, you have to look around a little bit and look for the thin profile needle bearing thrust bearing. So here's what I'm talking about. This comes as a set. You have just some flat shim type washers, and then you sandwich between the two of those. Get a focus on that. Come on, focus, you thing, you can do it. There's that. The ones, the ball bearings, there you can see that better, too fat, too much space. So these are a great thing to have if you can find the diameter that you need. So this is a 1/2 inch for the lead screw. If you want to put one by the motor, then you'll have to go with the diameter of that shaft. Here's one without the Z-axes on it, so I could show you the. This is your anti-backlash nut. I'm considering making one of these, designing one, and then just 3D printing the whole mess. I got to figure out where to get this spring from, but I was thinking this is not that big of a damn deal. So the way it's working here is, I don't know, you probably can't see up in there, but this is threaded up inside there, and it's split, and then this collar and the spring help hold all the plastic. It just sort of grips it around the lead screw. And oh, by the way, if you don't know what backlash is when you move down a piece of like a gearing or a threaded rod, the teeth on the thing that the worm drive here, the screw is pushing, they're towards the back, and so it's pushing, and then when the thing starts to turn the other direction, there's a moment in time, just a small moment, where it goes the other direction, and this will just sit here waiting for this side to hit it. So then it'll hit up against this side, and now it'll start coming this way. So it's that little play in the steering that we have to get rid of, because you can't have a mill that's going to have any kind of accuracy slopping a little bit, delayed every time it goes back and forth. When you move the mill, you want it to move back and forth and back and forth and back and forth, not back, wait, forth, back, oops, you know, that's going to be bad. So these, you find these online for, the reason I want to make it myself is they're a bit expensive. You can find them online for anywhere from like maybe $15, $16 to, I've seen them for up to like $36, I think. And there's not a whole lot. Look around on YouTube. There's a guy that makes his own too, or shows you how to make your own. Another piece of the reinforcement, I guess you'd say, of the whole thing. Make sure that you have collars on here and bearings. You might even put a thrust bearing in here again. And then over on the other side, we have again one of these flexible jaw couplers here. This has a little bit of a gap between there, so it doesn't rub on the metal, which would, you would think, give it the ability to go back and forth, but this is squeezed onto the shaft of the motor here, and so it will not go this way. Now, these Lovejoy couplers, sorry, the flexible jaw couplers, they will pull apart because of that spider inside there. They're just pressed together here. So now I could take this, and I could pull this, and it would just tear this part right apart. So that is why we have this here. This holds the rod from going out. So make sure that you include something like this in your designs. Alright, so if you look in here, there you can see there is another bracket with an anti-backlash nut on it. So this is the y-axis, at least what we're calling the y-axis. And so we're going to have one on each side, one here and one over here. Then we'll have another one inside there, pretty much exactly the same setup, and then again the one up here in front, and this is what's going to trap the lead screw for the Z-axis going up and down. No, this is not a table, but it absolutely could be. This is from another mill that it hasn't been put together on. This is what the Z-axis up here will look like. So here's the motion. Back and forth here, back and forth here. Alright? So this, after getting this and seeing this, as long as it's not terribly too big, I guess you could space these out. This could be a really decent contraption for making yourself a moving table. Consider that. All right, so that's it. Thanks for watching and everything. It was all pretty much an impromptu video, so you know, I think maybe in the future, if I want to make a video, I might want to make a video on all the parts and pieces of CNC. There are kind of a lot of things like that already out there, so maybe. But this was just a little insight into things that I do, and kind of what else I got going on in the world besides all these other projects that I'm not finishing. So thanks again for watching. I hope you enjoyed it. Questions below, and I'll see you next time.